What if faster-than-light travel is no longer just science fiction? For decades, the speed of light has stood as the ultimate limit of the universe. But now scientists say a new breakthrough may have changed the conversation in a way no one expected. Is humanity finally one step closer to warp drive, or is this discovery being misunderstood? In this video, we break down what the new research actually says, what it means for physics, and whether faster-than-light travel just got real. Before we begin, make sure to like this video, subscribe to the channel, and turn on notifications for more deep space mysteries and science breakthroughs. News of faster-than-light travel often arrives first as a bright surface event. It appears on screens in short summaries, in simplified drawings of folded space, in polished animations of stars streaming past a silent ship. The claim seems easy to picture. A human craft leaves one star and reaches another in a span that fits within a lifetime. Distance, which usually stands like a vast dark plane, seems to soften. Space seems less fixed. The old limit seems to bend. Yet the scientific landscape around such a claim remains wide, quiet, and exacting. Before any machine, before any field equation, before any speculative design, there is the setting itself. There is the United States research world, the broader international scientific community, the long public memory of science fiction, and above all the physical scale of the universe through which any real journey must pass. The outermost region of this topic is not a laboratory. It is not yet mathematics. It is scale. Between Earth and the Moon, distance already stretches far beyond ordinary travel. Between Earth and the Sun, the span grows so large that ordinary speech begins to lose feeling. Beyond the outer planets, the solar system opens into distances that are difficult to hold in mind all at once. Beyond that lies interstellar space, where the nearest star system beyond the Sun sits more than 4 light-years away. A light-year is the distance light travels in 1 year through vacuum. It is not a measure of time in this use, but a measure of separation. Even the nearest target beyond the solar system is set across a gulf so large that conventional propulsion struggles to appear meaningful against it. This is why the phrase faster than light carries such force. It does not merely promise a better engine, it seems to promise relief from the structure of cosmic distance itself. In ordinary travel, higher speed reduces travel time in a simple way. A faster aircraft crosses a continent sooner than a slower one. A faster spacecraft reaches a planet sooner than a slower one. But in interstellar travel, the gap is so immense that even large gains in speed do not easily turn a remote destination into a near one. A craft moving far beyond the performance of present rockets would still face years, decades, or longer for one crossing. The public imagination notices this burden, and so it remains highly responsive to any report that a deeper solution may have appeared. Within that reaction, one stable fact continues to govern the outer boundary of the subject. In modern physics, light in vacuum sets the known local speed limit for matter, energy, and information. This principle belongs to special relativity, one of the central achievements of 20th century physics. It does not arise as a suggestion or a convention. It emerges from the observed structure of nature. Countless experiments support it. Particles with mass require more and more energy. As they approach light speed, and under known physics they do not cross that limit through ordinary acceleration. This does not mean that science closes itself to every new idea. It means that any claim touching this limit enters a region of exceptional scrutiny. That scrutiny becomes especially important because the phrase faster than light can hide several very different ideas beneath one smooth surface. One meaning suggests a ship moving through local space faster than a beam of light would move through that same local region. Another meaning suggests that space itself may change shape or evolve in such a way that a path becomes effectively shorter, while the ship inside its immediate surroundings never outruns light locally. These are not minor differences in wording. They belong to different physical pictures. Public discussion often blends them together because both seem to produce the same human outcome, namely arrival sooner than expected at a distant place. Science cannot afford that blending. It must separate the pictures carefully before it decides what has or has not changed. The emotional power of the topic also comes from time. Human lives are short beside stellar distances. Civilizations measure history in centuries and millennia, while stars endure across spans vastly longer. A human journey to another star under familiar propulsion appears burdened not only by energy and engineering, but by generations' biology, isolation, and endurance. The appeal of a deeper breakthrough therefore carries a calm but persistent human wish beneath it. It is the wish that the universe may be traversable in a more intimate way than present tools allow. The wish is understandable. The wish is not itself evidence. Still, it forms part of the atmosphere around every new claim. In recent years, some theoretical papers have drawn renewed attention because they revisit so-called warp drive geometries, including new attempts to make them more physically consistent. A geometry in this context means a description of space-time shape. Space-time is the combined structure of space and time used in relativity. Some of these papers do not announce a finished vehicle and do not demonstrate that matter or information has truly travelled faster than light in a practical setting. Instead, they explore whether certain mathematical descriptions of warped spacetime can avoid earlier problems that seemed severe or fatal. This is a meaningful scientific development. It is also far from the same thing as a working starship. The distance between a better equation and a usable craft remains immense. The outer setting therefore contains two different motions at once. One motion belongs to media culture and imagination. It moves quickly. It compresses nuance. It turns a revision in a theoretical model into a dramatic threshold moment. The other motion belongs to science. It moves slowly, not from lack of interest, but from discipline. It asks what exactly the new result shows. It asks whether the assumptions are physical. It asks whether the model remains stable. It asks whether the required matter can exist in the needed form. It asks whether the proposal stays below the speed of light in a local sense, even if it changes the larger path. It asks whether the claim concerns mathematics, natural law engineering, or only language. Seen from this outermost region, the breakthrough is real only in a narrow and careful sense. It may be real as a change in what theorists can consistently write down within general relativity. It may be real as a reduction of one obstacle that earlier warp models faced. It may be real as a sign that the subject deserves continued formal study rather than immediate dismissal. But the grander public meaning, the image of routine, faster than light passage between stars, remains unproven. Observations indicate that no experiment has yet shown a spacecraft outrunning light through local space. It remains uncertain whether any warp-like geometry could ever be created sustained, controlled or occupied by matter in the way the most hopeful renderings suggest. So the topic begins where all large scientific ideas begin in the open air between wonder and restraint. The universe remains large. The nearest stars remain far. Light remains the known standard against which motion is measured. A new paper may shift the map of possibility at the edge of theory, but the outer horizon of interstellar travel still stands vast and dark, with distance itself lying quietly across it like a deep, cold sea. The known speed limit of the universe does not begin as a rule painted onto space from the outside. It arises from the structure of space and time themselves as modern physics describes them. In the early 20th century, this structure receives one of its clearest forms in special relativity. The theory begins from a simple and severe insight. The laws of physics appear the same for observers moving at constant speed relative to one another, and light in vacuum is measured to have the same speed in all such frames. From these points, ordinary habits of thought begin to change. Time no longer flows in exactly the same way for everyone. Length no longer remains fixed in every state of motion. Simultaneity, which seems so natural in daily life, turns out to depend on the state of motion of the observer. This shift is not a matter of language alone, it is part of the measured behavior of nature. Clocks in motion do not keep time exactly as clocks at rest do. Particles moving at very high speed behave in ways that agree with relativistic prediction. Signals do not outrun the limit set by light in vacuum. The speed of light becomes more than a property of lamps or stars. It becomes a deep conversion factor in the fabric of space-time, tying intervals of time to intervals of space. In older ways of thinking, speed is just distance divided by time. In relativity, the very definitions of distance and time depend on motion in a linked way, and light marks the invariant boundary that remains the same through those changes. For matter with mass, this boundary has a particular consequence. As a massive object is pushed to higher and higher speed, its relativistic energy increases without bound as it approaches the speed of light. In plain words, each further gain becomes harder than the last. The limit is not like a hill that a stronger engine may someday crest. It is built into the mathematical form of motion itself. Under known physics, no finite supply of energy accelerates a massive object, from below light speed to light speed, and still less beyond it through ordinary local motion. This is why the common phrase breaking the light barrier does not fit established theory. Nature does not present a thin line waiting to be crossed. It presents an asymptotic edge always approached, never reached by mass moving through local space-time. Light itself behaves differently because the particles of light photons have no rest mass. They are not gradually pushed upward to the speed of light by an engine. They simply travel at that speed in vacuum. This also helps clarify an old source of confusion. When someone says that nothing can go faster than light, the claim applies in the context of local motion and signal transfer in vacuum as described by relativity. It does not mean that all things everywhere always separate from one another at less than light speed in every possible cosmological setting. In the expanding universe, distant galaxies can recede from one another effectively faster than light because space itself expands. This does not allow a local spacecraft to outrun a nearby beam of light, nor does it allow signals to bypass the local causal structure. The distinction is subtle, but it is central. A causal structure is the pattern of what can influence what. In relativity, light traces the boundary of causal connection. An event can affect only those future events that lie within its permitted region of influence. That region is often pictured as a light cone, a geometrical way of marking the future and past reachable by signals moving at or below light speed. The image is simple but powerful. It means that the speed of light is not merely about travel time, it is about order, cause, and consistency. If ordinary information could move faster than light through local space, different observers could disagree on the sequence of cause and effect in troubling ways. Under some arrangements, an effect could appear before its cause. Physics therefore treats the light limit not as an inconvenience, but as part of the stable ordering of the world. This is the point at which the modern warp idea begins to take shape, though not yet in detail. It does not usually try to claim that a ship inside its own immediate surroundings outruns light in the local sense. Instead, it asks whether the geometry around the ship might be altered so that the craft rides within a moving distortion of space-time. The ship in that picture may remain locally at rest, or moves slowly relative to the space immediately around it, while the larger geometry carries it across an effectively shortened route. This concept belongs not to special relativity alone, but to the broader framework of general relativity, where space-time can curve and change. Even so, the reason such ideas attract attention is precisely because the local speed limit remains so firm. Warp proposals arise as attempts to work around the limit without directly violating the local rule. That local rule has been tested with great care. Particle accelerators drive matter to speeds extremely close to the speed of light, and the observed behavior agrees with relativity. Precision clocks carried on aircraft and satellites reveal the predicted adjustments of time. Space missions rely on relativistic corrections for accurate navigation and timing. The theory is not a poetic description surviving by habit. It is a practical account of reality used every day in systems that would drift into error without it. This practical success matters because any new claim about faster-than-light travel must not merely sound plausible. It must either remain fully consistent with this body of evidence or show with equal rigor where a deeper theory changes the rules. Thus, the cosmic speed limit stands in a very particular way. It is not simply the claim that light happens to be fast. Many things in nature are fast. It is the claim that local space-time has an invariant causal speed, and that matter with mass does not cross it by ordinary acceleration. This is why recent theoretical work on warp spacetimes receives attention, even when it remains subliminal. Subliminal means below the speed of light. If a warp-like configuration can exist while respecting known energy conditions, and while keeping local motion within accepted bounds, then it may shift how physicists think about motion through curved spacetime without overturning special relativity. The limit remains. What changes is the space of mathematical possibilities around it, so this second region of the subject stays exact and quiet. Light in vacuum remains the measured standard. Massive bodies do not pass it through local motion. Cause and effect remain ordered by that boundary. The dream of reaching distant stars therefore does not first encounter a shortage of courage or imagination. It encounters the deep architecture of space-time itself, where speed is not merely velocity, but the shape of what the universe allows. Beyond the formal speed limit, beyond the equations that define it, there stretches the physical setting that makes the problem of interstellar travel feel so severe. It is the broad cold region between stars, a region often called empty, but never truly empty. This emptiness is the next outer layer of the subject. It is the medium through which any real crossing must pass, and its calm appearance can hide the scale of the difficulty. Interstellar space does not behave like an ocean with waves, or like air with weather, or like a road laid ready for motion. It is thinner than any vacuum made on Earth, darker than any ordinary night, and yet it still contains matter radiation, magnetic fields, and above all distance in its purest practical form. In daily life, empty space seems like the absence of things. In astronomy, it is better understood as a region where things are extraordinarily sparse. A few atoms may drift through a volume that by human standards would seem immense. Dust grains may be scattered across spans so wide that they almost never meet. Light from distant stars crosses these reaches for years, centuries or longer, carrying energy, but not building a pathway. The medium exists, but it does not offer support. It does not provide traction. It does not reduce the burden of travel. It simply makes clear that motion between stars means carrying a vehicle across a vast domain that gives almost nothing back. This is one reason why the speed of light matters so deeply in space travel. If the universe were crowded and structured in some denser way, perhaps routes might be built from station to station, or matter, might be drawn upon continuously along the way. In interstellar space, the vehicle must largely bring its own means of survival, its own energy strategy, its own shielding, and its own timescale. The emptiness magnifies every problem because it offers little to work with. It turns distance into duration, and duration into exposure. Even when no planet, moon, or star lies nearby, the journey is not free of interaction. It remains exposed to radiation, to rare but dangerous particles, and to the long consequences of moving through a medium that is nearly absent yet never fully absent. The nearest stars make this plain. Their light arrives across years. A signal sent outward does not return quickly with news. A craft moving far below light speed would spend a large share of a human lifetime in transit, even on the most modest interstellar mission. If the craft moved at a small fraction of light speed, the trip would still remain long enough for engineering reliability, biological endurance, and accumulated hazard to become central issues. Thus, interstellar vacuum is not merely the background to the story. It is part of the pressure that drives theorists to ask whether the geometry of space-time itself might offer a different kind of route. Yet the vacuum between stars is not a channel already shaped for such a route. Under known physics, space-time in these regions is close to flat on local scales, meaning it is not strongly curved by nearby massive objects. Flat in this context does not mean two-dimensional. It means that the geometry of space-time over modest local regions behaves nearly like the space-time described in special relativity. Light moves along the usual paths. Cause and effect remain ordered in the usual way. No natural corridor appears in the vacuum that simply carries a ship across the stars by hidden convenience. A warp proposal therefore does not discover a pre-existing tunnel in ordinary interstellar space. It imagines a way to alter the geometry itself. This distinction matters. The problem of interstellar travel is often spoken of as a propulsion problem, as though a strong enough engine alone might gradually solve it. But the deeper difficulty appears when distance becomes so great that even dramatic propulsion advances still leave the traveller inside an enormous span of nearly featureless vacuum. In that regime, the journey is not defined only by thrust. It is defined by space-time separation. The universe does not merely place destinations far apart in a geographical sense. It places them within a causal geometry that resists quick crossing by ordinary motion. A useful way to see this is to compare nearby travel with stellar travel. Within the solar system, long missions are difficult, but they remain legible to present thinking. A spacecraft may use fuel gravity, assists careful navigation, and years of patience. Planets and the Sun provide reference points. Energy from sunlight may still matter, and communication delays, though significant, remain manageable on human planning scales. In interstellar space, those supports recede. Sunlight fades into weakness. Navigation becomes more self-contained. Communication delay stretches into years. The craft enters a region where the universe offers fewer landmarks and less practical assistance. The vacuum becomes not just empty space, but a measure of isolation. This isolation also clarifies why headlines about faster-than-light breakthroughs spread so readily. They appear to promise not only speed, but escape from the emptiness between stars. They seem to say that the long dark interval may no longer be master of the journey. But the physics does not yield so easily. Even if some warp-like geometry were possible, it would not mean that the vacuum itself has changed character. It would mean that a localized region of space-time has been shaped in a controlled way within that vacuum. The emptiness remains, the scale remains. What changes if such a change can ever be achieved is the path laid through the geometry. Observations and theory alike indicate that interstellar space is quiet but not simple. High-energy particles cross it. magnetic structures thread through it. Radiation from stars, galaxies, and the early universe passes through it continuously. Dust and gas, though sparse, can still matter over long distances and high speeds. A craft moving rapidly enough would not move through perfect nothingness, but through a thin and relentless environment where even tiny amounts of matter can become serious hazards when relative speed becomes extreme. This is another reason ordinary high-speed interstellar flight appears difficult. The medium is thin, yet across great spans it is still enough to matter, so the vacuum between stars teaches a calm lesson. The outer problem of interstellar travel is not only that stars are far away, it is that they are far away across a region that offers almost no support, little forgiveness, and no natural exemption from relativistic order. Interstellar emptiness does not merely separate worlds, it preserves the full meaning of their separation. It is within this quiet and severe setting that the idea of shaping space-time begins to gain its strange appeal, not as fantasy alone, but as a response to the sheer stillness and length of the cosmic gulf. Space in ordinary experience seems passive. It seems to wait while objects move through it, as a room waits while a person walks across the floor. Time seems similarly fixed, flowing evenly, whether anything happens or not. General relativity changes this picture. In this theory, space and time together form a single physical structure, and that structure does not merely contain matter and energy. It responds to them, it bends, it stretches, it guides motion. The broad arena of the universe becomes active not in the sense of having intention, but in the sense of having physical shape that changes under physical conditions. This curved arena is the next region of the topic because any serious discussion of warp travel must first stand inside this wider view of how space-time behaves. General relativity begins from a simple recognition that gravity is not most deeply described as a hidden pulling force acting across empty space. Instead, gravity appears as geometry. Matter and energy influence the curvature of space-time, and that curvature influences how matter and light move. A planet circles a star not because an invisible line pulls it through a flat background in the old way of thinking, but because the planet follows the natural paths available in curved space-time around the star. Light, though massless, also responds. It bends near massive bodies. Time itself runs differently in stronger gravitational fields than in weaker ones. Clocks deeper in gravity tick more slowly than clocks farther away. These effects are not decorative details, they are measured features of the world. A geometry in this setting means the way distances, durations, and paths are defined in spacetime. In flat spacetime, the kind used in special relativity, the shortest or straightest paths behave in a familiar relativistic way. In curved spacetime, those paths change. Objects in free fall follow what are called geodesics. A geodesic is the nearest thing curved spacetime has to a straight line. It is not always straight in the visual sense. It is the natural path that a freely moving body follows when no other force acts on it. Around Earth, a falling stone, an orbiting satellite, and an array of light passing near the Sun each reveal this principle in different forms. This matters because the idea of a warp configuration does not arise from ordinary mechanics. It arises from the fact that general relativity allows spacetime itself to take many forms, provided those forms satisfy the Einstein field equations. These equations relate geometry to stress energy, the combined description of matter, pressure, momentum, and energy density. In plain language, they say that space-time tells matter how to move, and matter tells space-time how to curve. The sentence is simple, but its consequences are immense. Black holes, gravitational waves, cosmic expansion, time dilation in gravity, and the bending of light all follow from this framework. The theory is not marginal or speculative. It is the standard description of gravity across modern physics and astronomy. Within this curved arena, empty space is no longer truly featureless. Even vacuum can possess geometry. A region with no nearby matter may still belong to a larger curved structure shaped by distant bodies or cosmic expansion. Curvature can also move and change. Gravitational waves, for example, are ripples in space-time curvature generated by accelerating masses under suitable conditions, such as merging black holes or neutron stars. These waves travel outward and can be measured. Their detection confirms with great precision that space-time is not merely a concept placed over reality. It is part of reality itself, capable of dynamical behavior. Once this is accepted, the basic appeal of warp ideas becomes easier to understand. If space-time can curve and if geometry governs motion, then perhaps motion across great distances need not depend only on pushing a ship harder through locally flat space. Perhaps one might instead alter the geometry around the ship. This does not yet say that such alteration is possible in practice. It only says that general relativity allows the conversation to begin on mathematical grounds. Without curved space-time warp ideas would have no home. With curved space-time they at least have a formal language. Still, the curved arena is not a blank permission slip. General relativity is generous in one sense and severe in another. It is generous because it admits a wide range of exact and approximate solutions, some of them far stranger than ordinary intuition would ever guess. It is severe because those solutions must satisfy precise relations between geometry and stress energy, and because not every mathematical solution corresponds to matter or conditions that nature can actually provide. A strange geometry may be easy to write in compact symbolic form, while remaining impossible to create, impossible to stabilize, or dependent on forms of energy that have no known macroscopic realization. This is why the move from curved space-time in general to warp travel in particular remains so difficult. The theory also preserves local order even while allowing large-scale curvature. At every small enough point in space-time physics looks locally like special relativity. This is a deep feature of the theory. A freely falling observer in a sufficiently small region can treat local space-time as approximately flat. Light locally still marks the causal boundary. Matter locally still does not outrun it by ordinary motion. This means curved space-time does not erase the speed limit explained earlier. It embeds that limit into a richer setting. Warp concepts therefore do not begin by destroying relativity. They begin by working within its broader gravitational form. This local flatness is important because it helps explain why curved spacetime can appear to offer a path around a limit without directly breaking it. If a region of spacetime as a whole changes shape, then distant points may be connected in a different effective way, even while local laws remain intact at each small location. Whether this can ever be done in a controlled physical manner is another matter. At this stage, only the arena is visible. The arena says that geometry is physical, that geometry can change, and that motion depends on geometry. It does not yet say that any desired geometry can be built, so this region remains broad, austere, and exact. Stars curve space-time. Planets follow the resulting structure. Light bends. Clocks drift apart in their rates when gravity differs. Black holes reveal extreme curvature. Gravitational waves show curvature in motion. The universe in general relativity is not a stage with fixed boards beneath the actors. It is a flexible fabric of distance and duration, shaped by the contents it contains. Within that flexible fabric lies the only serious conceptual opening through which warp travel can even be imagined. The opening is not a machine and not a promise. It is the curved arena itself where geometry becomes physical, and the path between places becomes at least in principle something nature can shape. Within the wide mathematical freedom of general relativity, one proposal becomes especially famous because it gives a clear formal picture of how a journey across great distance might occur without a ship locally outrunning light. This is the Alcubierre warp drive introduced in the 1990s as a specific solution to the Einstein field equations. The idea stands at the threshold between disciplined theory and powerful imagination. It does not begin with an engine in the ordinary sense. It begins with a region of space-time shaped so that the space behind a central craft expands, while the space ahead contracts. The craft placed within a central bubble of nearly flat space-time is not pictured as firing itself through surrounding space faster than light. Instead, the surrounding geometry itself changes in such a way that the bubble moves. This picture is often simplified into a verbal image of surfing on space-time, though the image can mislead if taken too literally. Water waves move through water, but space-time curvature is not a substance in that simple sense. Still, the comparison survives because it captures one useful feature. The ship inside the bubble does not rely on ordinary thrust to reach superluminal effective travel across large distances. The proposed motion comes from the structure of space-time around it. If space behind grows and space ahead shrinks, then the bubble can move relative to distant points, even while the ship inside remains locally at rest with respect to its nearby surroundings. The elegance of the idea lies partly in this separation between local and global description. Locally inside the central region, the ship and its occupants may experience conditions close to ordinary inertial motion. Inertial motion means motion without felt acceleration, like drifting smoothly in deep space. This is one reason the concept attracts so much attention. A conventional craft pushed to extreme speed may subject itself and its passengers to severe accelerations, immense energy demands, and relentless exposure to the hazards of long travel through interstellar vacuum. A warp bubble appears on paper to replace the brute struggle of propulsion with a more subtle strategy. It does not fight the distance head-on. It attempts to reshape the distance. To see why this matters, it helps to distinguish between motion through space and motion of space in a geometrical sense. In everyday life, only the first seems familiar. A car moves down a road, a planet moves around a star, a spacecraft moves away from Earth. The Alcubierre proposal asks whether the second kind of description can be used in a localized engineered way. In cosmology, the large-scale expansion of the universe already shows that space can change its scale over time. Very distant galaxies may recede from one another because the metric of space changes not because each galaxy simply flies through local space like a projectile. The warp idea borrows some of this conceptual freedom, but compresses it into a localized traveling structure. A metric is a rule that defines intervals in space-time, telling physics how to measure distance and duration. In the Alcubierre solution, the metric is chosen so that a bubble-like region forms around a central path. Inside that region, space-time stays relatively mild. Around it, the geometry changes in a directed way. In front, space contracts. Behind, space expands. The result is a moving pocket of space-time carrying the ship. In popular accounts, this becomes a shortcut without a tunnel. The destination is not brought closer in the ordinary Euclidean sense, but the geometry of the route changes so that the bubble can cross what would otherwise be a forbidding span. The formal beauty of the proposal does not mean it is automatically physical. A solution to the equations of general relativity can exist mathematically while remaining far from natural realization. This is where the Alcubierre drive becomes both fruitful and difficult. It serves as a proof of concept in one limited sense. It shows that the equations of general relativity are rich enough to describe a warp-like geometry with apparent faster-than-light travel relative to distant observers while preserving local relativistic order inside the bubble. That alone is remarkable. It tells physicists that relativity does not forbid all imaginable warp pictures at the level of pure geometry. But a geometry is not yet a machine, and a metric is not yet a material. The ship in the central region is also not the active source of the motion in any ordinary mechanical way. The bubble is the true object of interest. The vehicle becomes in a sense a passenger of the geometry. This is one reason why so many practical questions gather immediately around the proposal. What creates the bubble? What holds its shape? What initiates its motion? What determines its speed? What stops it? What prevents destructive forces from forming at its edge? What kind of stress energy must occupy the surrounding shell? These are not secondary engineering details added after the main idea. They are part of whether the idea can ever move beyond mathematical existence. Still, as a theoretical landmark, the Alcubierre proposal remains important. It gives the warp conversation a concrete center. Before it, faster-than-light travel in relativity often lives either in pure impossibility arguments or in scattered speculative notions. With it, the discussion becomes more focused. A specific space-time geometry can be examined. Its properties can be tested. Its flaws can be identified. Variants can be proposed. Energy requirements can be estimated. Causal issues can be studied. Stability can be analyzed. The subject shifts from vague desire to defined mathematical object. That shift also explains why newer papers continue to return to the concept. They do not simply repeat the original proposal. They often ask whether some part of its structure can be modified to reduce its deepest problems. Can the bubble be shaped differently? Can the required matter be made less exotic? Can the apparent motion remain subliminal while preserving useful properties? Can the geometry be embedded in more realistic conditions? Each question grows out of the Alcubierre framework because it supplies the canonical form of a warp drive in modern physics. So this region of the topic holds one clear idea in view. The Alcubierre proposal is not a rocket made faster. It is not a claim that matter simply blasts through space beyond light speed. It is a geometrical construction in which a central craft rides inside a moving distortion of space-time with expansion behind and contraction ahead. The concept is calm, elegant, and exact on paper. It also stands at the edge of practicality, where a solution may be real in mathematics while remaining profoundly uncertain in nature. The warp bubble, once introduced as a broad idea, begins to show its true character at its boundary. The central region in the original picture is comparatively gentle. It is the shell around that region that carries the burden of the geometry. This shell is the next inward layer of the topic because it is where the smooth image of a ship riding through altered space-time becomes a harder physical structure with edges, gradients, and limits. A boundary in space-time is not like the metal wall of a vessel. It is a region where the metric changes from one form to another, where flatness gives way to distortion, and where the motion of the bubble is encoded into the changing shape of the surrounding geometry. In simple renderings, the bubble looks like a clean sphere moving silently through the stars. In actual analysis, its boundary is more demanding. The shell is not just a surface that separates inside from outside. It is the place where space-time curvature becomes concentrated in a directional way. The central cavity is meant to remain mild enough for a ship and crew to occupy. The far outside region is closer to ordinary surrounding space-time. Between these lies the shell, a finite zone where the transition is carried. This transition cannot be arbitrary. It must satisfy the field equations, and it must do so while producing the desired effect of forward motion of the bubble. A shell in this context means a surrounding layer in which the stress and curvature are significant. The word does not imply a solid material wall. It describes where the active structure of the warp geometry resides. If the ship is the quiet center, The shell is the working skin of the space-time distortion. It is there that the expansion behind and contraction ahead become organized into one moving configuration. It is there that energy, density, pressure, and momentum flow must take on the forms demanded by the metric. The calm central picture depends entirely on this more difficult outer layer. As soon as the shell is examined, a new issue appears. The bubble is not simply a region carried forward by a hidden current. Its front and rear are not symmetric in physical meaning, even if the diagram appears symmetric in shape. The rear region is associated with expansion of space, while the front region is associated with contraction. These are not decorative labels. They indicate that the geometry must change differently in different directions to maintain the effective motion of the bubble. The shell therefore carries directionality within it. It is not merely a spherical cushion. It is a structured distortion, aligned with the intended path of travel. This directional structure leads to one of the most serious conceptual difficulties in warp physics, the problem of horizons. In relativity, a horizon is a boundary beyond which events cannot influence an observer in the usual causal way. The best-known example is the event horizon of a black hole, though the warp case is different in form and purpose. In some analyses of superluminal warp motion, a horizon appears at the front of the bubble. If that occurs, signals from the central region may not be able to reach the leading edge in the way needed to control it. A craft inside the bubble could then find itself carried by a structure whose forward boundary it cannot directly command once the motion is underway. This matters because a controlled vehicle requires more than passive existence. It must be startable, steerable, and stoppable. If a horizon isolates the front edge, then the very part of the geometry that defines the path ahead may lie beyond local influence from the occupants. The bubble becomes less like a navigated machine and more like a prearranged solution whose control is uncertain. This is one reason why horizon structure receives so much attention in warp studies. It is not only a mathematical curiosity, it reaches into the question of whether the bubble could ever function as a usable transport system. The shell also raises questions of thickness and smoothness. If the transition between inner calm and outer space-time is too abrupt, curvature grows severe. If it is too broad, the geometry may become inefficient or require even larger regions of stress energy. The shell must be shaped with care. Too sharp a boundary may invite instability or extreme tidal effects. Tidal effects are differences in gravitational influence across distance. In ordinary life, tides on Earth arise because gravity from the Moon and Sun varies slightly from one side of the planet to the other. In a warp context, rapidly changing curvature across the shell could produce severe gradients that no material object or living body would tolerate. A gentle interior therefore depends on a shell that does difficult work without passing destructive consequences inward. Another problem emerges from interaction with the outside world. If the bubble moves through interstellar space, even though the ship inside is locally sheltered from ordinary acceleration, the shell itself defines how external particles and radiation meet the geometry. Analyses have suggested that particles and fields may accumulate shift in energy or behave in complicated ways near the front region. The exact behavior depends on the model, but the general lesson is steady. The bubble boundary is not an abstract line drawn on a diagram. It is the active interface between the interior and the external universe. Any realistic treatment must ask what happens there to matter, light, and information. For this reason, the shell is often where enthusiasm begins to narrow into technical realism. The central image of a quiet craft in a protected bubble remains attractive because it seems to free the traveller from the usual violence of high-speed propulsion. Yet the protection is not magic. It must be bought by the shell, and the shell is where the theory becomes demanding. It must store the distortion, maintain the asymmetry between front and back, preserve the inner calm, interact consistently with the exterior, and avoid causal structures that make guidance impossible. Every one of these requirements presses inward from the boundary. Some newer studies attempt to reshape the shell so that certain old difficulties are softened. They may alter the stress distribution, choose different bubble profiles, or accept only subluminal motion to avoid the harshest horizon problems. These adjustments show that the shell is not a fixed feature of one historical paper. It is the living technical center of warp research. When scientists say that a newer warp solution is more physical, they often mean that its shell is described by stress energy conditions that look less pathological than before, or that its causal structure is less self-defeating. So this inward layer reveals the first deep cost of the warp idea. A bubble is not mostly defined by the emptiness inside it. It is defined by the demanding shell around it. The boundary must carry the geometry, the direction, the causal order, and the interaction with the wider universe. The more calm the center appears, the more exacting the shell becomes. In that sense, the bubble's promise is written not in its quiet interior, but in the difficult skin of curved space-time that surrounds it and tries to hold the entire concept together. Once the shell of the warp bubble comes into view, the next inward layer is the matter or energy that must sustain it. Here the subject becomes more severe. In general, relativity curvature does not arise for free. Geometry is tied to stress energy, and stress energy is the accounting of what exists in a region: energy, density, pressure, momentum, flow, and related physical quantities. A warp bubble is therefore not only a shape in space-time, it is a demand placed upon matter and energy. The original Alcubierre proposal becomes famous not only because it offers a formal route around ordinary distance, but because it appears to require a kind of source that nature has not been shown to provide on useful scales. This source is often described as negative energy density, and it becomes one of the central barriers in the whole subject. Energy density is the amount of energy present in a given volume. In ordinary physical situations, energy density is positive. A warm gas, a beam of light, a moving fluid, a magnetic field, a chunk of rock, and an ordinary spacecraft all contribute positive energy density. Pressure may be positive or negative depending on context, and stresses may pull or compress in different directions. But the broad expectation in classical physics is that matter behaves in ways that satisfy certain energy conditions. These are mathematical rules that express in compact form the idea that physically reasonable matter should not be too strange. They help preserve the normal relation between energy, motion, and curvature. The classic warp solution strains these expectations. In many treatments, the shell around the bubble must contain regions where the measured energy density is negative for certain observers. Negative energy density does not mean simply less energy than hoped for, or energy counted relative to an arbitrary baseline in an ordinary engineering sense. It means that the local stress energy behaves in a way unlike familiar macroscopic matter. Such behavior is not wholly unknown in theoretical and quantum settings, but it does not resemble any ordinary substance that can be stored in tanks shaped into walls or accumulated in large durable amounts. The warp idea therefore collides with a basic physical question. Even if the geometry can be written down what is the bubble made of in energetic terms, this is where the language of exotic matter enters the subject. Exotic matter in this context does not mean mysterious material from deep space or some unknown metal beyond the periodic table. It means matter or effective stress energy that violates the usual classical energy conditions. The word exotic refers to its unusual gravitational behavior, not to its origin. In the warp case, the shell may need this exotic character in order to create the expansion behind and contraction ahead while keeping the inner region mild. The geometry appears to ask for a source that pushes space-time in directions ordinary matter does not naturally push it. The seriousness of this problem becomes clearer when one remembers that relativity has already been tested in many ordinary and extreme settings. Stars, gas clouds, black holes, compact remnants, radiation fields and laboratory systems all seem to respect classical energy conditions at macroscopic scales in the broad sense relevant here, except where quantum effects introduce subtle, local departures. No astrophysical object has been observed behaving like a stored reservoir of large-scale negative energy, ready to shape a warp shell. No engineering method exists for gathering such a source in the required form. The warp bubble in its original superluminal style therefore appears to demand not merely better technology, but a fundamentally unfamiliar physical resource. This barrier is not an afterthought added by skeptical critics. It emerges from the equations themselves when the required curvature is translated back into stress energy. The field equations do not permit geometry to be specified without cost. They ask what source produces it. For black holes, stars, planets, and gravitational waves, the sources or effective dynamics connect to known physics. For a classic warp bubble, the bookkeeping turns severe. The desired motion is purchased by stress energy that seems to step outside the family of ordinary classical matter. The proposal remains mathematically coherent as geometry, but its physical footing becomes uncertain. At times, discussions of this problem become blurred by hopeful language about energy in general, as though enough energy of any kind might solve it. The issue is sharper than that. A large supply of ordinary positive energy does not automatically replace the need for negative energy in a given space-time solution. Geometry depends not only on magnitude, but on sign direction and distribution. 1,000,000 times more fuel in the ordinary sense does not simply turn a forbidden stress pattern into an allowed one. The warp shell asks for a specific profile of energy and stress. Quantity alone does not answer that demand. Older estimates of the required energy also become famous for their extremity. Depending on the version of the bubble and the assumptions used, some calculations suggest energy scales so vast that they exceed any plausible human capacity by enormous margins. Later refinements and alternative bubble shapes sometimes reduce those estimates, but reduction does not by itself remove the deeper problem. Even a smaller requirement remains physically inaccessible if the sign and form of the energy are wrong. Thus, public discussion sometimes mistakes an improvement in numerical estimate for a solution to the fundamental source problem. The real obstacle is not only that the amount may be huge, it is that the needed stress energy may not be available in the required macroscopic form at all. For this reason, many recent warp studies shift in tone. Rather than declaring faster than light travel solved, they ask narrower questions. Can a warp-like geometry be found that uses only positive energy density? Can the motion remain below light speed while preserving some useful feature of a bubble? Can the shell be built from matter models that at least resemble known fluids or fields? These are important questions precisely because the original negative energy requirement is so difficult. A paper that finds a subluminal warp solution respecting classical energy conditions is not a trivial retreat. It is a serious attempt to move the subject from formal fantasy toward a more physically legible regime. Still, the old barrier remains a fixed landmark in the field. Superluminal warp travel in its classic form continues to be linked with exotic stress energy. Observations indicate that no experiment has produced such a source on meaningful scale. It remains uncertain whether nature permits sustained macroscopic negative energy distributions of the kind the original bubble seems to require. This uncertainty is not a small gap in engineering. It is a wound at the centre of the idea where geometry asks the universe for a kind of support the universe has not clearly shown. So the inward journey reaches a stern conclusion here. The shell is not just curved, it must be fed. And what it seems to ask for in the classic superluminal picture is not ordinary matter, not ordinary fuel, and not merely more power. It asks for exotic stress energy, with negative energy density in the right place and form. That demand turns the graceful image of a warp bubble into a harder physical question, one that has shaped almost every serious discussion of the subject ever since. The demand for negative energy leads naturally inward to the smaller and stranger domain where modern physics has at least in limited ways encountered something that resembles it. This domain is quantum theory. At the classical level, matter behaves with the ordinary signs and constraints that make the warp problem so severe. At the quantum level, the vacuum is no longer a simple emptiness. It becomes a state with fluctuations, temporary correlations, and measurable effects that have no direct parallel in classical intuition. This is the next inward layer of the story, because it is here that the phrase negative energy stops sounding purely impossible and begins to appear in narrow and delicate form within accepted physics. A quantum vacuum is not a box of nothing. It is the lowest energy state of a field, and even in that lowest state the field retains structure. In simple language, it cannot sit in perfect stillness at every point all at once. Fluctuations remain. These fluctuations do not mean that particles pop in and out in the crude visual sense often used in popular accounts, though that image points toward a real idea. The true picture is more careful. Quantum fields possess unavoidable uncertainty, and the uncertainty leaves observable consequences. One of the most famous examples is the Casimir effect, in which two very closely spaced conducting surfaces alter the allowed quantum modes between them and produce a measurable force. This effect is often cited in warp discussions because it shows that quantum systems can create regions where energy relative to a chosen vacuum reference behaves in ways that differ from classical expectation, yet the difference between such effects and a warp bubble is immense. The Casimir effect occurs over tiny distances under carefully arranged laboratory conditions. It does not yield a large free reservoir of negative energy ready to be shaped around a spacecraft. It shows that quantum theory allows local departures from naive classical positivity in controlled circumstances. It does not show that such departures can be scaled up indefinitely, stored, stabilized, or distributed in the precise shell-like pattern that warp geometry seems to require. The lesson is important, but it is often overstated. Quantum theory opens a narrow conceptual door. It does not build the machine beyond it. This distinction becomes even clearer through the idea of quantum inequalities. These are theoretical limits showing that negative energy, where it appears in quantum field theory, is tightly constrained in magnitude, duration, and arrangement. In plain terms, nature does not seem to allow an observer to collect an arbitrarily large region of negative energy and hold it in place for an arbitrarily long time. Small negative contributions may occur, but they are accompanied by balancing conditions. A pulse of negative energy may need to be compensated by positive energy elsewhere or later. The universe appears to permit these strange local features only under strict bookkeeping. This bookkeeping matters greatly for warp concepts, because a stable travelling bubble seems to allow for something far more durable and extensive than a fleeting quantum departure. Quantum theory therefore gives both hope and restraint at once. It weakens the claim that negative energy is completely alien to physics. At the same time, it strengthens the claim that such energy is not freely available in the form warp advocates would most like. A narrow allowance in a microscopic setting does not easily become a broad permission at macroscopic scale. This is a recurring lesson in physics. Many effects that are real and important at atomic or subatomic scales do not simply magnify into engineering tools when enlarged. Coherence is lost, control fails, instability grows, or the supporting conditions become impossible to maintain. The warp problem may belong to this pattern. Another subtle point appears here. In general relativity, gravity responds to the full stress-energy tensor, not only to a simple scalar amount called energy. Pressure and stress matter too. This means one cannot move carelessly from a quantum result that seems to allow a negative local energy density to the conclusion that a practical warp shell is therefore within reach. The required space-time curvature depends on a full structure of stresses and flows arranged with direction and persistence. A tiny local quantum effect measured in a laboratory setup is not yet the correct gravitational source for a moving bubble. The shape of the requirement remains exacting even after the word quantum is introduced. The quantum vacuum also raises a deeper caution about language. Popular descriptions often speak as though empty space is full of usable energy waiting to be tapped by a future civilization. There is some truth behind the image in the sense that fields have vacuum structure and that the universe is not classically empty. But usable energy is a technical concept. A background state may contain physical properties without offering a practical energy source that can be extracted at will. Likewise, the presence of rare negative energy effects does not imply that space-time can be sculpted on demand. Physics does not move from strange possibility to applied control by verbal enthusiasm alone. Even so, quantum theory keeps warp discussions alive because it prevents the classical verdict from becoming entirely final. If negative energy were forbidden without exception, the classic warp picture would sit even farther from serious study than it already does. Because quantum field theory allows limited exceptions, researchers can ask whether there exist more subtle arrangements than the first analyses assumed. They can test bounds, examine semi-classical effects, and ask whether combined matter models might imitate some desired curvature without fully violating the rules. These are real scientific questions. They have not produced a usable warp drive. They have, however, kept the subject within the outer edge of legitimate theoretical investigation. Semi-classical gravity. The framework often used here treats matter fields quantum mechanically, while space-time itself remains classical. This approach is useful but incomplete. It is not a finished theory of quantum gravity. As a result, there is an additional uncertainty in warp debates. Some questions may ultimately depend on a deeper union of quantum theory and gravity not yet achieved. Observations indicate that both theories work extremely well in their respective domains, but it remains uncertain how all extreme conditions should be handled when quantum effects and strong curvature must be treated together in full detail. This uncertainty does not rescue warp travel by itself. It simply means the final theoretical verdict may not rest entirely on present tools, so this inward layer is delicate rather than dramatic. Quantum theory does not deliver a starship hidden inside the vacuum. It offers something smaller and more austere. It shows that nature can, under controlled conditions, depart from classical expectations in ways that include negative energy-like behavior. It also shows that such departures are bounded, fleeting, and difficult to scale. The microscopic world allows strange whispers. The warp bubble seems to ask for a sustained and organized chorus. Between those two lies a great distance, not across the stars this time, but across the gap between quantum subtlety and macroscopic engineering. After the outer layers of distance relativity geometry shells, exotic stress and quantum limits have been laid in place. The recent claim of a breakthrough can finally be examined in its own proper region. Here the subject becomes narrower and more exact. The breakthrough does not consist of a spacecraft crossing to another star. It does not consist of an experiment showing matter or information outrunning light in a laboratory. It does not consist of a machine built and tested under controlled conditions. The advance lies in theory. More specifically, it lies in a class of recent studies suggesting that warp-like space-time configurations may be written in ways that avoid one of the oldest and harshest problems of the classic Alcubierre picture, namely the apparent need for negative energy density. This is why the claim matters. It is also why the claim must be stated with care. A breakthrough in theoretical physics often means that a previous impossibility has been softened into a narrower obstacle. It can mean that an argument once thought general is shown to depend on assumptions that may be relaxed. It can mean that a class of solutions once regarded as unphysical is found to include members that obey more acceptable conditions. This is the kind of change at issue here. Some recent warp studies describe subluminal bubble solutions supported by matter models that satisfy the weak energy condition, a standard requirement that in plain language says ordinary observers should not measure negative local energy density. This is a serious shift in the discussion because it moves part of warp theory away from the most troubling demand of exotic matter. The importance of the word subliminal must be held steadily in view. Subliminal means below the speed of light. In these newer models, the bubble does not achieve effective faster-than-light travel. It remains within the relativistic limit. Yet this does not make the work trivial. A warp-like geometry supported by positive energy is important because it shows that the broad concept of a moving space-time distortion is not automatically chained to the most pathological energy requirements in every possible case. In other words, some warp shapes may be more physically respectable than earlier versions, even if they do not deliver the dramatic outcome that popular headlines imply. This distinction between warp-like and faster-than-light is the core of the present breakthrough. The newer work suggests that one may be able to build on paper a compact region of altered space-time that resembles a warp bubble in structure, while remaining below light speed and while using sources closer to ordinary matter behavior. The mathematics may describe a central region carried by a shell of stress energy, without demanding large regions of negative energy density. That is a meaningful development. It tells physicists that the solution space of general relativity is richer and perhaps more physically forgiving in some regimes than the first famous warp proposal suggested. But it does not tell them that superluminal travel has become real in the everyday sense of the phrase. This is where public interpretation often drifts away from scientific meaning. A headline sees the words warp drive breakthrough and physically possible, then compresses them into a single message faster than light travel may have arrived. The actual theoretical meaning is much narrower. A certain mathematical family of warp-like metrics may include members that satisfy better energy conditions than the classic superluminal form. The achievement is real, but it lives inside formal gravitational theory. It does not abolish the causal structure of relativity. It does not show how to create the required space-time in a laboratory. It does not show how to energize control or stabilize a bubble around a vehicle. It does not prove that nature permits large engineered distortions of this kind outside paper models. The recent work also changes the emotional geography of the subject. For many years, warp travel discussions were easy to dismiss on one decisive ground. If the geometry always required large-scale negative energy, then the concept could remain mathematically interesting while physically remote. A subluminal positive energy solution complicates that dismissal. It says the conversation can no longer be sorted so quickly into fantasy and impossibility. There may be a middle ground in which warp-like motion exists as a legitimate object of theoretical study, even if the grandest, faster-than-light version still lies beyond established physics. This middle ground is narrower than the headlines promise, but wider than the older verdict allowed. At the same time, the breakthrough should not be stretched beyond its own region. A theoretical solution is a structured answer to the field equations under chosen assumptions. It is not a demonstration that suitable matter can be assembled, that the configuration is dynamically stable, or that an actual spacecraft can inhabit the geometry safely. Many exact solutions in relativity describe worlds or objects that are mathematically coherent, yet physically incomplete. Some require idealized matter. Some assume perfect symmetry. Some omit perturbations that may destroy the solution when realistic disturbances are allowed. Warp research must face all of these concerns. A newer solution that respects positive energy locally still has many gates to pass before it becomes a plausible engineering concept. There is also a deeper point about the word real. In physics, real can mean several things. A quantity can be real, mathematically meaning it belongs to a consistent solution. A phenomenon can be real, observationally meaning nature has been seen to do it. A mechanism can be real, experimentally meaning it has been created and measured under controlled conditions. A technology can be real, operationally meaning it performs useful work in the world. The recent breakthrough belongs mainly to the first of these meanings, and perhaps partly to the second only, in the sense that it remains consistent with the known structure of gravitational theory, rather than immediately defying it. It does not yet belong to the later meanings. This is not a small difference. It is the entire reason the subject remains open rather than settled. So the new work deserves both seriousness and restraint. It deserves seriousness because it refines the old picture in a physically important way. It deserves restraint because the refinement does not yet cross the great divide between formal possibility and applied reality. Observations indicate that no superluminal warp transport has been demonstrated. It remains uncertain whether any engineered warp-like structure can be generated sustained or stabilized with known matter. What has changed is narrower and more disciplined. A part of the old impossibility wall may not be solid in every subluminal case. That is enough to revive careful interest. It is not enough to declare that the stars have suddenly come within reach. The meaning of subluminal warp motion becomes clearer when the initial excitement of the breakthrough is set aside, and the idea is held in plain light. A subluminal bubble remains below the speed of light. This seems obvious, yet much of the public confusion around recent warp papers begins here. The word warp suggests victory over distance in the dramatic sense. It suggests arrival sooner than light itself could cross the same span. But a subluminal warp solution does not claim that. It claims something more limited and more technical. It describes a moving region of altered space-time whose speed as defined within the model remains within the accepted relativistic boundary. The geometry may still be unusual. The stress energy may still be arranged in a bubble-like form. The motion may still differ in character from ordinary propulsion. Yet the fundamental causal order of relativity remains intact. This matters because the light speed limit is not merely a performance benchmark. It is a structural feature of space-time. If a warp-like geometry remains subluminal, then it does not need to overturn that structure. It may still raise many hard questions, but it does not immediately collide with the same causal paradoxes that trouble superluminal motion. In a superluminal setting, cause and effect can become difficult to preserve across different observers, and horizons may appear in ways that make the bubble hard to control. A subluminal configuration, by staying beneath the local causal boundary, may avoid some of the harshest versions of these problems. It is therefore physically interesting, not because it has already solved interstellar travel, but because it may inhabit a region of theory where the equations and the causal structure are less hostile to one another. One can think of the difference in calm practical terms. A superluminal warp proposal attempts to leap over the deepest boundary in relativity, while still claiming consistency with local physics. A subluminal warp proposal does something more modest. It asks whether a compact directed distortion of space-time can move in a controlled way, without requiring impossible stress energy, and without crossing the boundary that physics guards most closely. If the answer to that narrower question is yes, then warp theory changes status. It no longer appears only as a dramatic scheme dependent on exotic loopholes. It begins to resemble a family of gravitational transport concepts still remote from engineering, but not automatically ruled out by the first principles that once seemed decisive. This does not mean the gain is merely philosophical. Even below light speed, a warp-like geometry could matter scientifically if it revealed new ways that space-time can be shaped by matter. It could matter if it clarified which energy conditions truly constrain moving distortions and which do not. It could matter if it showed that localized bubble can exist with more ordinary stress profiles than earlier proposals allowed. A positive result in these areas would enrich general relativity itself. It would refine how theorists understand motion compact curvature and the interplay between local flatness and global transport. The value of such work is not measured only by whether it leads directly to a starship. Fundamental physics often advances by understanding what kinds of structures are permitted in principle. Even when practical application remains very distant, still the limitations must be spoken plainly. A subluminal warp bubble does not make interstellar distance easy. If the bubble remains below light speed, then a trip to even the nearest stars still requires years, as measured by distant observers, and likely still requires immense energy and extraordinary control. The bubble may protect an interior from some kinds of acceleration stress, at least in ideal models, but it does not abolish duration. It does not erase the need to create the geometry in the first place. It does not provide an obvious source of power. It does not guarantee stability against perturbation. It does not solve shielding navigation or interaction with the sparse matter and radiation of interstellar space. The result is important within theory, while leaving the practical mountain largely standing. There is also a conceptual danger in assuming that any warp-like motion is automatically superior to advanced conventional propulsion. That is not yet known. A subluminal warp bubble might prove, even if theoretically allowed, far harder to create than a very fast ordinary spacecraft. It might require matter distributions or field controls so extreme that no realistic engineering path leads to them. It might turn out to be less efficient, less stable, or less scalable than other future propulsion concepts. The word warp carries a cultural weight that can hide this comparison. But physics does not award practical value to an idea because it sounds profound. It asks what resources are needed, what constraints arise, and whether the concept survives contact with real matter and real dynamics. Another reason subluminal warp matters is that it changes the burden of proof. In the old picture, critics could point to negative energy and say that the concept depends on a source not known to exist in usable form. In the newer picture, at least for some models, that criticism becomes less absolute. The question shifts from can such stress energy exist at all, to can such a configuration be generated, maintained and controlled with any plausible matter system. This is still a severe question, but it belongs to a different category. It is no longer a direct contradiction with a well-established classical energy condition. It is a challenge of construction dynamics and material realism. That is progress, though it is not triumph. The narrowing of the claim also restores a more careful meaning to the word breakthrough. A breakthrough need not mean that the destination has been reached. It can mean that the route has changed from impossible in one way to uncertain in another. In that sense, a subliminal positive energy warp solution is significant. It tells the field that one layer of impossibility may be less absolute than once believed. But because the solution remains subliminal, the oldest dream attached to warp travel remains untouched at its core. Faster than light motion across interstellar distances in the strong popular sense has not been demonstrated by this result. The dream survives, but the breakthrough belongs to the mathematics of allowed structures, not to the conquest of the light barrier, so this region of the topic settles into a quieter truth. Subliminal warp is not the dramatic ending of the story, it is the disciplined shrinking of one impossibility argument. It shows that a bubble-like space-time distortion may perhaps live within more ordinary energy rules than the classic superluminal case demanded. That is enough to keep theorists interested. It is not enough to say that light has been surpassed, or that the stars have suddenly become near. The breakthrough is real in the language of relativity, but its reality remains narrow, careful and still enclosed by the larger structure of known physics. A space-time solution on paper can appear calm and exact while hiding a deeper fragility. This next inward layer concerns that fragility. It is the question of what kind of matter model stands behind a newer warp-like solution and whether the resulting structure remains stable when treated as something more than a frozen equation. Stability is a quiet word, but in gravitational physics it carries enormous weight. A configuration may satisfy the field equations at one idealized moment and still fail as a physical object if small disturbances grow, if the source matter cannot hold its form, or if the structure collapses when realistic motion is allowed. The warp bubble once granted a more acceptable energy profile in some newer models must now pass through this narrower gate of persistence. A matter model is a simplified description of what fills spacetime in the equations. It tells the theory how energy, density, pressure and momentum are related. In ordinary astrophysics, a star may be modeled as a fluid, a neutron star may require a denser and more complex relation. An empty space may be modelled as vacuum with no ordinary matter present. In newer warp studies, theorists sometimes replace exotic negative energy shells with more conventional matter sources such as anisotropic fluids. An anisotropic fluid is a fluid whose pressure is not the same in every direction. This directional difference matters because the shell of a warp bubble is itself directional. It must support different geometric roles at the front, sides and rear. A perfectly ordinary isotropic fluid one that presses equally in all directions may not be able to maintain the needed form. The move towards such matter models is important because it brings the bubble a little closer to the language of known physics. A fluid is not an arbitrary mathematical device. It is one of the main ways large collections of matter are described across relativity and cosmology. But the comfort this language brings can be deceptive. A fluid in an equation does not automatically correspond to a substance that can be prepared, confined and manipulated in the real world. The pressures may be extreme. The directional stresses may be difficult to realize. The profile may have to be tuned with unreal precision. The fluid may need to flow in ways that are formally allowed and yet physically unstable. So the question becomes more specific. Even if the source looks less exotic in sign, does it behave well under disturbance? A disturbance can be almost anything that nudges a system away from ideal perfection. A tiny change in density, a slight asymmetry in shape, a passing wave, a mismatch between the assumed profile and the actual one. In stable systems, such disturbances remain bounded or fade away. In unstable systems, they grow. A star can remain stable for millions or billions of years because pressure and gravity balance one another over long spans. A collapsing cloud can be unstable, because gravity amplifies inward motion. A bridge can vibrate safely under small loads, or fail if oscillations feed upon themselves. A warp bubble, if it is ever to become more than a formal construction, must belong to the first class rather than the second. It must not fall apart as soon as the perfect symmetry of the equations is touched. This is a hard demand because the bubble is not static in the most interesting cases. It is meant to move. Motion introduces further complications. A moving space-time distortion must carry its stress-energy profile along with it, or continuously recreate it in a coordinated way. If the shell is made from an idealized fluid, then the fluid's internal dynamics matter. Pressure gradients may steepen. Shear may arise. Small mismatches in the front and rear structure may grow. The bubble could begin to deform, radiate energy, or collapse into a less useful configuration. The more compact and intense the curvature, the more serious such concerns become. A solution that exists only in exact equilibrium may provide little comfort if any real attempt to start it moving destroys it. The relation between matter and curvature also means that instability may feed back on itself. A small disturbance in the source changes the geometry. That changed geometry alters how the source moves. The altered motion then modifies the source further. This loop can either settle or run away. In some gravitational systems, such feedback produces ringing that gradually fades. In others, it drives collapse or explosive change. Warp research must therefore ask not only whether a bubble can exist at one moment, but how it responds to perturbation across time. This moves the subject from exact solutions toward dynamical analysis, where equations become harder and conclusions often become less forgiving. There is another layer of difficulty in the boundary between the interior and the shell. The interior is often meant to remain flat or nearly flat so that a ship may rest there without severe tidal stress. But if the shell is supported by matter with highly directional pressure, then any slight change in shell structure may leak inward as distortion. The protected central region may shrink, shift, or develop gradients of curvature that were absent in the ideal model. The very feature that makes the bubble attractive, the calm interior, may depend on a precarious balance across the shell. A stable interior therefore cannot simply be assumed. It must be earned dynamically. Some recent work on warp-like solutions is valuable precisely because it begins to address this more serious standard. It asks whether positive energy bubbles can be embedded in source models that are not obviously pathological. It studies whether certain profiles remain smooth and compact. It examines whether horizons are avoided in subliminal cases. Yet many of the deepest questions remain open. A mathematically admissible fluid model is not the same as a laboratory realizable medium. A smooth metric is not the same as a stable transport system. Observations indicate that no physical experiment has yet shown a macroscopic warp-like shell persisting under realistic perturbations. It remains uncertain whether any positive energy source capable of generating such a geometry would keep its shape once the full dynamics are allowed to unfold. This uncertainty is not a failure of the theory. It is the ordinary discipline of physics. Nature often permits ideal forms that are difficult or impossible to realize. A pencil can balance on its tip in principle, but not robustly. A fluid can form a delicate surface pattern that vanishes when the conditions shift slightly. A star can remain stable only within a certain mass range beyond which a different fate begins. The warp bubble may prove to belong to a similar class, one whose elegant existence in equations does not guarantee endurance as a physical structure, so this inward region becomes more intimate and more exacting. The issue is no longer simply whether the bubble requires negative energy. In some newer models, perhaps it does not. The issue is whether the matter source, often described through carefully chosen directional stresses, can actually support the geometry in time. The bubble must not merely exist, it must persist, it must tolerate disturbance, it must carry its own curvature without dissolving into instability. Here the dream of warp motion narrows further from allowed sign to lasting form, and the mathematics begins to ask whether the bubble can remain itself once the universe is allowed to touch it. Even if a warp-like bubble can be written with a more acceptable source, and even if that source can remain stable in principle, one further inward layer still stands between theory and transport. This layer is control. A space-time distortion is not useful merely because it exists. It must be generated, shaped, guided, and sustained. These verbs sound practical, but each hides a deep physical demand. A bubble is not like a shell built from metal and then left to drift. It is a state of geometry coupled to matter and energy. To create it would mean arranging stress energy in space with extraordinary precision. To guide it would mean altering that arrangement in time without breaking the structure. To sustain it would mean keeping the source profile within narrow bounds, while the bubble moves through a changing external environment. In this region, the question stops being what equations allow and becomes what control over nature would actually be required. Generation comes first. A warp configuration does not arise by ordinary motion alone. A spacecraft cannot simply accelerate until a bubble forms around it as a side effect. The geometry must be built. In general relativity, that means the stress energy responsible for the desired curvature must already be present in the right pattern, or must be driven into that pattern by some field or material process. If the shell requires compact regions of strong directional pressure, then those pressures must be established before the bubble can carry anything. If the model assumes a fluid source, then that fluid must be prepared in the right density profile and directional state. If the model assumes some field configuration, then that field must be arranged coherently across the whole bubble region. The first problem of warp engineering is therefore not speed, it is assembly of curvature. This assembly problem is more severe than the construction of an ordinary vehicle, because the object to be built is partly geometric. In ordinary engineering, matter is shaped into a machine that then acts on its surroundings. In a warp concept, the machine and the surrounding geometry are intertwined. The shell is not merely attached to the ship, it is the operative structure itself. A craft might sit in the middle, but the true device is the distribution of stress energy around it. This means the builder would need the ability to manipulate space-time indirectly through matter and fields, with precision far beyond any demonstrated technology. It is not enough to possess large amounts of energy. That energy must be placed in the right form at the right location, with the right directional character, and held there against drift and disturbance. Then comes steering. A moving bubble must know its path in more than the ordinary navigational sense. It must preserve the asymmetry between front and rear that gives it motion. If the contraction ahead weakens or shifts sideways, the path may deviate. If the expansion behind becomes uneven, the bubble may distort. If the shell thickens in one region and thins in another, the protected interior may move off-center or lose its calm conditions. Steering thus becomes a matter of live space-time management. One must not only know where the destination lies, one must continuously maintain the geometry that makes the route possible. In ordinary spacecraft guidance, a computer adjusts thrust or orientation based on sensors. The surrounding spacetime is treated as given. In warp guidance, spacetime itself becomes the quantity being adjusted. Sensors would need to monitor the bubble geometry, the shell profile, the interaction with external radiation, and sparse matter, and the state of the source fields or fluid. Control systems would need to respond without delay, large enough to let the bubble drift into instability. The engineering challenge therefore begins to resemble active control of a self-sustaining gravitational structure. Nothing in present aerospace practice approaches this directly. Humanity can measure space-time curvature with exquisite sensitivity in certain contexts, but measuring is not the same as sculpting, and sculpting is not the same as doing so in motion. Sustaining the bubble introduces the energy question in a more practical form. Even if a newer solution uses positive energy density, it may still require extraordinary amounts of energy or stress concentrated within a compact shell. The total magnitude may depend on bubble size, wall thickness, desired velocity, and the matter model assumed. A thinner shell can sharpen the geometry, but may demand more severe local stresses. A larger interior can hold a meaningful craft but may enlarge the total energetic burden. A faster bubble may increase the required gradients. These trade-offs suggest that warp control is not a single switch that turns on a convenient mode of travel. It is an ongoing energetic balance, likely delicate and expensive, in which shape, size, and motion remain tightly linked. Stopping the bubble may be even harder than starting it. A controlled transport system must not only achieve motion, but terminate it without destroying itself or its occupants. If the shell stores the distortion, then reducing that distortion must be done gradually enough to avoid violent transients. A transient is a temporary but potentially intense change during adjustment. In electrical systems, a transient can surge through a circuit when power changes. In a warp shell, a transient could mean abrupt reconfiguration of curvature, stress, and pressure. If not managed carefully, the bubble might collapse asymmetrically, releasing stored energy into the surrounding region or into the interior. Thus, arrival is not merely the endpoint of travel. It is another demanding phase of curvature control. The control problem is also inseparable from information flow. To command a system, one must be able to send instructions through it. Earlier concerns about horizons in superluminal bubbles point to a deeper principle. The geometry must remain causally manageable by those operating it, or by some external system able to influence the shell. A subluminal bubble may soften this problem, but it does not erase it completely. Control signals still have finite speed. Feedback loops still require time. The faster and tighter the geometry, the more severe the demand for rapid coordination across the shell. A warp system would therefore need not only energy and material support, but a causal architecture that allows it to govern itself without slipping beyond its own control bandwidth. This is why a positive energy subluminal warp result, important as it is, does not yet amount to practical transport. It shifts the source problem, but it leaves the control problem towering. Observations indicate that no known technology can generate compact directed space-time curvature on demand, let alone monitor and steer it in real time around a habitable interior. It remains uncertain whether any physical medium could support the needed feedback precision and stability simultaneously. The deeper one moves inward, the more the bubble resembles not a vehicle design awaiting funding, but a total redefinition of engineering itself, so this region becomes quietly decisive. A warp configuration may be permitted by equations. It may even avoid the most famous exotic matter objection in some limited cases. Yet to become real in the operational sense, it must be brought under control. It must be built as geometry guided, as geometry sustained as geometry, and dissolved as geometry. The theory asks whether space-time can in principle take a given form. Engineering asks whether that form can be commanded. Between those two questions lies a gulf almost as sobering as interstellar distance itself. One of the clearest ways to understand a difficult structure is to imagine its failure. This inward layer turns from operation to breakdown not for drama but for knowledge. In physics, collapse and instability often reveal more than ideal equilibrium. A star shows its inner balance when it begins to pulsate. A bridge reveals its hidden stresses when resonance builds. A fluid exposes its structure when smooth flow turns turbulent. In the same way, a warp-like bubble may disclose its deepest physical character, not only when it moves as intended, but when it distorts, radiates, or falls apart. Failure is not merely the end of function. It is a diagnostic event, a way the geometry speaks through change. A warp shell, if it exists, is a compact arrangement of stress energy and curvature. That arrangement must remain organized while resisting perturbation. If the organization weakens, the bubble may not simply vanish without trace. It may release the stored deformation of space-time into wave shocks or dispersing matter fields depending on the model. In general relativity, changing curvature can radiate outward as gravitational waves. A gravitational wave is a traveling ripple in space-time produced by changing mass-energy configurations with suitable asymmetry and acceleration. The great detections of recent years come from mergers of black holes and neutron stars, where immense masses move violently. A warp bubble would be very different in scale and structure, yet in principle its birth, deformation, or collapse could also generate such ripples if the changing geometry is strong and asymmetric enough. This possibility has drawn attention because it offers a path from pure theory toward observational consequence. A warp concept remains abstract so long as it is only a stationary metric on paper. It becomes a more physical object when researchers ask what signals it would produce while forming accelerating, oscillating, or failing. Some recent studies explore whether a collapsing or disturbed warp configuration might emit gravitational wave patterns distinct from those of more familiar astrophysical events. The hope is not that such a signal has already been identified in nature. No such detection has been confirmed. The value lies in turning the idea into something testable in principle. A theory that predicts no possible signature at all remains hard to compare with the world. A theory that predicts a characteristic failure signal has stepped closer to empirical science. The details matter here. A stable, isolated bubble moving perfectly steadily might radiate little or not at all depending on the model and frame used. But real systems are not perfectly steady. They begin, they adjust, they interact with environments, and they end. Any start or stop introduces time dependence into the geometry. Any asymmetry in the shell or source can couple to outgoing disturbances. If the shell is supported by a fluid-like source, then fluid modes may oscillate and feed energy into the curvature. If the bubble encounters irregular external conditions, even the sparse matter and magnetic structure of interstellar space could perturb it. The exact consequences remain model-dependent, but the general lesson is firm. Breakdown is not a separate afterthought. It is built into the life cycle of any dynamical warp structure. There is also an important safety meaning in collapse. A bubble that fails gently is very different from one that fails violently. In ordinary engineering, this distinction can decide whether a system is manageable. A material that cracks slowly offers warning. A pressure vessel that bursts without warning does not. For a warp shell, gentle failure would mean that the curvature relaxes in a way that does not produce extreme tidal gradients, destructive radiation, or sudden compression of the interior. Violent failure could mean the opposite. The shell might dump energy into surrounding space-time or into the bubble interior. External particles and radiation that had interacted with the front region might be released in concentrated form. The calm central region might cease to exist before occupants could respond. These possibilities are not yet established outcomes, but they frame the seriousness of the problem. A transport concept is not credible until its failure modes are understood. The interaction of failure with horizons and control also deserves attention. If a bubble's front region is hard to influence directly, then an instability developing there may outrun corrective action from the interior. Even in subliminal cases where the harshest horizon problems may be softened, feedback still takes time. A disturbance at one point in the shell changes the geometry elsewhere, only after signals and stresses propagate. During that delay, the instability may amplify. This is why dynamic simulations, not just static solutions, are essential. Equilibrium answers whether the bubble can exist. Failure analysis asks whether it can survive its own imperfections. Gravitational wave predictions from warp collapse remain especially interesting because they translate an unfamiliar transport idea into the language of observable astronomy. Modern detectors are built to notice tiny changes in distance caused by passing space-time ripples. Their confirmed sources so far are violent astrophysical systems of known kinds. A warp-related signature, if one ever existed in nature, or in some future experiment, would likely require careful separation from many other possibilities. It would not look like a simple label floating above the data. It would have to be identified through waveform structure duration, frequency content and consistency with a physically plausible source model. The challenge is immense. Still, the mere fact that such questions can be asked signals maturation in the field. Warp theory ceases to be only about whether a ship can go somewhere. It becomes also about what the universe would register if such a geometry were created or destroyed. Failure analysis also strips away some of the romance attached to the word breakthrough. A configuration that can be written down but not safely terminated is not a transportation system. A bubble that collapses into damaging radiation or intolerable curvature is not a practical vehicle even if it achieves elegant motion for a time. By studying breakdown, researchers force the concept to answer to the same standard as any serious technology. How does it behave when it is imperfect? How does it respond when something goes wrong? What observable trace does it leave when it cannot maintain itself? These are sober questions, and the warp idea must pass through them as surely as any aircraft reactor or spacecraft would. So this inward layer reveals motion through its ending. The bubble is no longer judged only by the grace of its ideal form, but by the character of its collapse. In the changing shell, in the release of curvature, in the possibility of emitted gravitational waves, the geometry becomes legible as a physical process rather than a static dream. Observations indicate that no warp failure signal has yet been identified. It remains uncertain whether any future experiment or astronomical survey will ever see one. Yet the search for such signatures marks a real step inward, because it asks the theory to expose itself under stress, where the truth of a structure is often most plainly seen. At this depth in the subject, the argument becomes quieter. Most of the bright surfaces have already fallen away. The headlines are behind. The clean image of a ship inside a smooth bubble is behind. The first excitement over a new theoretical paper is behind. What remains is the present scientific consensus, a region shaped not by one claim alone, but by the accumulated habits of careful physics. Consensus does not mean full agreement on every technical point. It means a broad shared judgment about what is established, what is plausible, what remains speculative, and what has not yet earned belief. In the case of warp travel, that judgment has become more nuanced in recent years. It is no longer as simple as saying that every warp-like configuration is immediately unphysical. Yet it remains far from saying that faster-than-light transport has entered the world of demonstrated science. The first part of the consensus is steady. Special relativity and general relativity remain foundational and strongly confirmed. Locally, matter and information do not outrun light in vacuum. The causal structure of space-time remains one of the most trusted features of modern physics. No laboratory experiment, no astronomical observation, and no engineering demonstration has shown a vehicle signal or controllable physical system achieving superluminal transport in the ordinary strong sense. This point is not under active collapse. It remains the baseline on which all further discussion stands. The second part of the consensus is more subtle. General relativity is rich enough to allow unusual spacetime geometries, including wormholes, horizons, cosmological expansion, and warp-like metrics. The existence of such solutions in the mathematics is real. The theory is not a narrow machine that permits only bland or familiar worlds. For that reason, it has long been known that one cannot dismiss every strange transport concept by intuition alone. A geometry may look impossible in common language and still exist as a formal solution. Warp research lives in this opening. It studies whether particular compact distortions of spacetime can exist under conditions that do not immediately violate the core structure of known physics. For many years, the consensus about classic superluminal warp drives remained severe. The best-known forms appear to require exotic stress energy, especially negative energy density in ways that are not supported by any known macroscopic source. They also raise concerns about horizons control stability and interaction with surrounding matter and radiation. These concerns are not decorative objections. Together they make the classic faster-than-light warp bubble appear physically remote. Consensus therefore continues to treat superluminal warp travel as speculative in the strongest sense. It is not merely unbuilt, it is unsupported by demonstrated source physics and burdened by deep theoretical obstacles. What has changed is narrower. Some recent theoretical work suggests that warp-like configurations may exist in subluminal regimes while satisfying more ordinary energy conditions. This does not erase the old obstacles for superluminal travel, but it does modify the broader landscape of what a warp-like metric can mean. A moving spacetime distortion no longer appears tied in every case to obviously forbidden negative energy matter. That is why physicists who follow the subject take the recent work seriously even when they remain cautious. The field has not crossed into practical transport. It has perhaps crossed from one kind of impossibility argument into a more refined set of open questions. This refinement matters because science often advances by replacing a blunt no with a structured maybe. A blunt no says the proposal violates known law in a direct and general way. A structured maybe says some versions are ruled out, some versions remain formally allowed, and the next task is to determine whether the allowed versions are dynamically stable, materially realizable, and empirically meaningful. Warp theory now sits closer to the second state than before, but only in limited domains. The consensus is therefore neither dismissive in the old absolute tone nor permissive in the popular dramatic tone. It is careful. It says the theory space is richer than once assumed, while the engineering and physical realization remain entirely unproven. Another part of the consensus concerns language itself. Physicists usually distinguish sharply between a mathematically consistent solution, a physically plausible matter source, and a realizable technology. Outside the field, these categories are often blurred into one. A new solution appears and people say travel just became real. Within the field, real is divided. A metric may be real as an exact solution. A matter model may be real as a formal source satisfying selected conditions. A phenomenon becomes more real when it yields robust observational consequences. A technology becomes real only when it can be built, controlled, and repeated. Warp research has not yet travelled through all these meanings. It has moved at most from formal curiosity toward greater physical legibility in a few subliminal cases. There is also broad agreement that many decisive questions remain open. Can positive energy warp-like bubbles survive perturbation? Can they be formed from realistic matter rather than idealized fluids? Can they be started and stopped without destructive transience? Can they be scaled beyond tiny theoretical constructs? Can they remain causally controllable? Can any signature of their creation or collapse be distinguished from more ordinary gravitational phenomena? Observations indicate that these questions are still unanswered. It remains uncertain whether the more promising newer models are merely elegant mathematical objects or early signs of a deeper physical possibility. The consensus then is not a verdict of arrival. It is a disciplined map of uncertainty. It accepts the reality of the equations, the seriousness of the newer subliminal results, and the continuing strength of relativity's causal limits. It rejects the idea that a headline alone can convert a refined theoretical paper into a practical, faster-than-light craft. It permits interest. It withholds conclusion. It narrows the old impossibility claim in one region while leaving the grander dream beyond demonstrated reach. So this inward layer settles into a sober shape. Warp research is no longer only a story of impossible exotic matter and immediate dismissal. Nor is it a story of starships suddenly stepping out of theory into the night between suns. It is a field at the edge of accepted gravitational study with a few newer results that have made the edge more interesting and less easily ignored. The strongest version of the dream true faster-than-light travel remains speculative and unsupported. The narrower result that some warp-like geometries may be more physically respectable than once believed stands as the real change. Between these two truths lies the present consensus, calm, exact, and still unresolved. At the innermost point of the subject, the meaning of the word real becomes the final question. The journey has moved from distance to relativity, from geometry to shells, from exotic energy to quantum limits, from new theoretical results to stability and control, and finally to consensus. Now it turns inward once more, not into a new physical region, but into the interpretation of all that has been seen. What does it mean in science for faster-than-light travel to become real? The answer does not lie in a single experiment or a single equation. It lies in a chain of conditions that must all hold at once, each one grounded in the same disciplined view of nature. A concept is first real when it exists without contradiction inside a well-tested theory. In that sense, warp-like geometries have achieved a kind of reality for some time. General relativity permits them as mathematical solutions. The newer work refines that reality by showing that some of these geometries may satisfy more acceptable energy conditions in subliminal cases. This is not a trivial step. It moves the idea from a narrow corner of theory into a somewhat broader one. It means the concept is no longer defined only by its most extreme and least physical features. Yet this first level of reality is also the most limited. Many structures exist comfortably in mathematics, while remaining absent from the physical world. The next level of reality appears when a concept is tied to matter and energy that nature actually provides. A geometry becomes more than an abstract shape when it can be sourced by physical fields or materials that obey known laws and can exist in stable forms. Here the warp idea remains uncertain. The newer models that avoid negative energy in some cases bring the concept closer to this level, but they do not complete the transition. A matter model written in equations is not yet a material that can be prepared, confined, and sustained. The stress energy must not only be allowed in principle, it must be achievable in practice. At present, no such realization has been demonstrated. A further level of reality arises when a system can be produced, controlled, and repeated. This is the level at which technology begins. A phenomenon is no longer only a feature of nature, it becomes a tool. It can be built again, adjusted, measured, and used for a purpose. In this sense, faster-than-light travel is not real. No warp bubble has been created. No controlled space-time distortion has carried a craft across a measurable distance. No system has been shown to start, steer, and stop such a configuration safely. Observations indicate that the subject remains entirely within theory at this operational level. Beyond this lies the level that the human imagination most often reaches for. It is the level of routine use where a concept becomes part of the ordinary functioning of a civilization. Aircraft electrical power and communication networks belong to this category. They are not merely possible, they are reliable and widespread. Faster-than-light travel in this sense is not only unreal, it is far from the conditions that would make it real. The gap between a refined theoretical solution and a dependable transport system is vast. It includes not only physics, but materials control systems, energy infrastructure safety, and integration into a broader technological world. The recent breakthrough therefore occupies a very specific place along this chain. It strengthens the first level of reality by refining what the equations allow. It may hint at a path toward the second level by showing that some warp-like geometries do not immediately demand exotic negative energy. It does not reach the third level of controlled creation, and it is far from the fourth level of routine use. To say that faster-than-light travel has become real would be to compress all these levels into one. Science does not permit that compression. It distinguishes them carefully because each level requires its own evidence. There is also a deeper meaning of real that lies in understanding. A concept becomes real in a scientific sense when it clarifies the structure of the world even if it is never built. Black holes were once only theoretical solutions. They became more real when their consequences were understood, and more real still when observations matched predictions. Even before direct imaging, their gravitational influence was measured in stars and gas. Warp theory may follow a similar path in a limited way. It may never produce a transport system, yet it may still teach physicists about the limits of space-time engineering, the role of energy conditions, and the behavior of compact curvature. In that sense, the idea contributes to reality by refining knowledge. At the innermost point, the excitement that began at the surface settles into a quieter recognition. The universe has not changed in response to a headline. Light still marks the causal boundary for local motion. Interstellar distances remain vast. Space-time remains curved by matter and energy in accordance with tested theory. What has changed is more delicate. A small region of theoretical space has opened slightly. A previously rigid barrier has shown signs of structure rather than uniform solidity. The word breakthrough applies to that subtle shift, not to the immediate transformation of travel across the stars, so the final view is calm. Faster-than-light travel has not become real in the sense that a ship may now cross from one star to another within a human lifetime by means of a built and controlled warp drive. What has become more real is the understanding that warp-like geometries may be more physically nuanced than once believed, at least in subliminal forms. The idea has moved inward from dismissal to qualified consideration, from simple impossibility to structured uncertainty. It remains enclosed by the larger architecture of relativity, energy, stability, and control. Within that enclosure, it continues as a disciplined question rather than a finished answer, a careful exploration of what space-time might allow and what nature may ultimately refuse. In the quiet after the final layer, the subject settles into a slower rhythm. The vast distances between stars remain unchanged, stretching in silence across the dark. The speed of light continues to mark the measured pace of signals and motion in the local world. The equations of relativity hold their form, linking geometry to energy with patient precision. The newer theoretical work rests within that framework, a small adjustment in what may be written and understood, not a sudden opening of the cosmos to easy passage. The idea of shaping space-time lingers as a distant possibility defined more by its constraints than by its promise. Matter must still take the forms that physics allows. Energy must still be arranged with care. Stability must still be preserved against disturbance. Control must still be achieved across a structure that is itself part of the fabric of the universe. Each requirement stands quietly, neither yielding nor closing, simply present as part of the world as it is known. In this stillness, the meaning of progress becomes gentle. A concept grows more real, not by sudden transformation, but by narrowing uncertainty, by refining questions, by tracing the boundary between what is permitted and what is not yet seen. Warp theory now rests closer to that boundary, shaped by new insight yet held by the same deep laws. The stars remain far. The path between them remains long. The understanding, however, has moved slightly inward, and it remains there steady and unresolved within the calm structure of the universe.